All right, let's do this. We're about to go on a pretty wild ride through the entire story of physics. And what you're going to see is that it's not just a bunch of random flashes of genius. Nope, it's a connected story where every single discovery was like a stepping stone for the next one. I mean, just think about that. From a simple apple falling from a tree to the microchip in your phone, it's all connected. This isn't just going to be a history lesson. It's a story about a chain reaction of ideas where each link forged the one that came next. So, where do we start? Well, we gotta start with a guy who basically wrote the first rulebook for how the universe works, Sir Isaac Newton. He's the one who gave us the tools, the language to finally understand why things move. And at the heart of it all is this incredibly simple yet powerful idea: force equals mass times acceleration. All that really means is, if you push on something, it speeds up. And the more stuff, or mass, it has, the harder you've got to push. That's it. This is the absolute bedrock of what we call classical mechanics. And the power of this, it's everywhere. Think about shooting a basketball. With Newton's laws, if you know the push from your hand, the pull of gravity, even a tiny bit of air resistance, you can predict that ball's path with basically 100% certainty. Is it going to be a perfect swish? Or, uh-oh, is it going to hit your neighbor's car? Newton's math can tell you. Then you've all heard the story, right? The apple. Whether it actually bonked him on the head or not, who knows? But the idea it sparked was world-changing. Newton had this massive realization. What if the force pulling that apple down to the ground was the exact same force keeping the moon circling the Earth? And this led him to his law of universal gravitation. Basically, anything that has stuff, or mass, is pulling on everything else with mass. So you, me, the Earth, the sun, we're all pulling on each other. And yeah, bigger things pull harder. But here's the really cool part, the kicker. Distance matters a lot. As things get further apart, the pull gets way, way weaker. It follows something called the inverse square law. Okay, and this is a perfect time to clear something up that trips a lot of people up: the difference between mass and weight. Your mass is just the amount of you, the stuff. That number is the same whether you're on Earth or the moon. But your weight, that's just gravity's pull on your stuff. So on the moon, with less gravity, you'd weigh a whole lot less. Which leads to one of my favorite physics jokes. You're not overweight, you're just on the wrong planet. So Newton absolutely nailed the rules for the big stuff, things we can see and touch. But his work was the perfect stepping stone. It opened the door to a whole new mystery. What about the invisible forces? How can something move without anything physically touching it? That was the next big puzzle. Okay, so here's Newton's law of gravity in all its mathematical glory. Don't worry about the letters, just look at the shape of it, how it's structured. Burn that image into your brain for just a second. Now, let's jump forward more than a century. Here's the formula for the force between two electric charges. Take a look. Does that ring any bells? Would you look at that? It's basically the same equation. This was a mind-blowing moment in physics. It's like the universe was reusing its own code. The rule that governs planets orbiting the sun is almost identical to the rule that governs the static shock you get from a doorknob. This was a massive clue, a huge signpost pointing to some deeper, hidden connection. And the guy who followed that signpost was James Clerk Maxwell. And what he found was honestly kind of freaky. He realized that electricity and magnetism aren't two different things at all. They're a team. A moving magnet, it creates an electric field. And a moving electric charge, yep, that creates a magnetic field. They're just two sides of the very same coin, something he called electromagnetism. And this beautiful dance, this constant back and forth between the two fields, it creates this chain reaction that shoots outward as a wave, an electromagnetic wave. And you know what we call the part of that wave that our eyes happen to be able to see? We call it light. But it's so much more. It's the radio waves bringing you music, the microwaves heating your lunch, and yeah, it's the Bluetooth signal connecting your headphones to your phone as we speak. Time to zoom way, way in. You know, it turns out reality is kind of like one of those Russian nesting dolls. You start with molecules, right? You open them up and inside you find atoms. Okay, cool. But then you look inside the atom and you find a tiny little core, the nucleus, made of protons and neutrons with electrons zipping around it. And you think you're done, but nope, the journey keeps going. You crack open a proton and what's inside? Even tinier things called quarks. This whole incredible family tree is what we now call the standard model of particle physics. It's our best map of what everything is made of. We know what atoms are made of, but then another giant came along. A guy who wasn't just going to add a new chapter to the rulebook, he was going to tear the whole thing up and rewrite it. His name, of course, was Albert Einstein. And this is where everything we thought we knew got turned completely on its head. Einstein looked at Newton's idea of gravity and said, "Sorry, but that's not quite right." He proposed that gravity isn't a force pulling things together. No, he said that massive objects like the sun literally bend and warp the very fabric of space and time around them. So the Earth isn't being pulled by the sun. It's just rolling along the straightest possible path through a curved universe. Just let that sink in for a second. Now, how on earth did he get there? Well, it started with one really wild idea. The only thing in the entire universe that moves at the same speed for everyone, no matter what, is light. So picture this. You're on a super fast train and you turn on a flashlight. From your point of view, the beam shoots away at the speed of light. Makes sense. But for someone watching from the side of the tracks, that beam is also moving at the speed of light, not the speed of light plus the speed of the train. How is that even possible? The only way the math works is if time itself has to slow down for you on the train. Your clock is literally ticking slower. Time isn't fixed, it's relative. And out of this completely new way of looking at the universe came probably the most famous equation ever written. You know the one, E equals mc squared. What it means is just profound. It means that mass, stuff, and energy aren't separate things. They're two sides of the same coin. Mass is just an incredibly, unbelievably concentrated form of energy. And just how much energy are we talking about? Well, that c squared part, the speed of light squared, is a gigantic number. So it means a tiny, tiny amount of mass is equal to a staggering amount of energy. To put it in perspective, converting just 1 gram of mass, about the weight of a paperclip, perfectly into energy would release the same power as 21.5 kilotons of TNT. That's the secret behind everything from nuclear power plants to atomic bombs. But here's the ironic twist. Einstein's own work on light accidentally opened a kind of Pandora's box, a doorway to a new part of physics that he himself was never really comfortable with. It was a world that governs the incredibly tiny, a place where all the common sense rules we know just fall apart. Welcome to the weird, weird world of quantum mechanics. And I mean it when I say the rules down here are bizarre. Get this. A particle, like an electron, doesn't just have one location. It exists in a cloud of possibilities. Here, there, everywhere, all at once. We call that superposition. But the crazy part is, the instant you try to look at it, to measure it, it snaps into just one single spot. It's as if it knows you're watching. And these tiny things can act like solid little particles 1 minute and spread out waves the next. It's just strange. All this weirdness leads to one of the most famous ideas in all of science, Heisenberg's uncertainty principle. Think about it like this. You're trying to take a picture of a baseball flying past. If you use a really fast shutter, you get a super sharp image, right? You know its exact position, but you have no idea how fast it was going. Now, if you use a slow shutter, you get a long blur. You can tell its speed and direction from the blur, but you have no clue where it was at any exact moment. The uncertainty principle says that this isn't just a problem with our cameras, it's baked into the fabric of reality itself. The universe simply will not let you know a particle's exact position and its exact motion at the same time. The more you know of one, the less you know of the other. Okay, let's just pause and look back at the journey we've been on. It's all stepping stones, right? We started with Newton, who gave us this clockwork, predictable universe. That was the foundation. Then Maxwell stood on his shoulders and unified electricity and magnetism. Einstein then took that next giant leap, completely changing our picture of space, time, and gravity. And in doing so, he accidentally unlocked the door to the quantum world, the weird, fuzzy reality that, believe it or not, is what makes the microchips inside the device you're using right now actually work. You see, every single step was built on the one before it. It's one continuous, amazing, interconnected story. And the best part is, every time we find an answer, it just opens up a dozen new, even more fascinating questions. The journey is so far from over, which just makes you wonder, what's the next stepping stone going to be? And what new, unbelievable reality is it going to show us?